Hello friends, now we discuss the formula for radial velocity. So let us suppose that moving there is a moving particle which moves on a curve. At time t, this particle is at point P, and after del t time this particle goes at the point Q. Now we suppose that let at time t the particle is at point P, and after del t time it moves at the point Q. Here we can see there is a particle which moves on a curve. At time t, the particle at point P, and after del t time, the particle is at point Q. Now we suppose that here r theta, this is the polar coordinate of P point. So this radius vector OP, this is equal to small r, and angle XOP, this is equal to theta. Angle XOP, this is equal to theta here. Now suppose that the polar coordinate of Q be r plus del r and theta plus del theta. So the radius vector OQ is equal to r plus del r, and angle XOQ, this is equal to theta plus del theta. So this angle is theta plus del theta. Here we can see that a moving particle when at point P, after del t time this particle goes at the point Q. The polar coordinate of PB are theta, so radius vector OP is equal to small r, and angle XOP, this is equal to theta. After del t time, when the particle is at the point Q, so the polar coordinate of QB r plus del r and theta plus del theta. So radius vector OQ, this is equal to r plus del r, and angle XOQ, this is equal to theta plus del theta. Now we find here angle POQ. So angle POQ, this is equal to angle XOQ minus angle XOP, this is equal to theta plus del theta minus theta. Theta plus del theta minus theta. So this theta is cancelled out, this is equal to del theta. Here we can see that angle POQ, this is equal to angle XOQ minus angle XOP, so this is equal to del theta. Here we can see that this angle is equal to del theta. Now we draw perpendicular QL from Q on the radius vector OP. Here we draw a perpendicular QL from Q on OP. Here we can see that triangle OQL, this is right angle triangle. So angle, here we can see that triangle OQL, this is the right angle triangle. Right angle triangle. Now we find here cos del theta. So cos del theta, this is equal to base upon hypotenuse. So base is OL here and hypotenuse is OQ. So this is OL is OQ cos del theta. Now we know that radial velocity is the component of velocity along the radius vector. So when we find here radial velocity, this can be written as limit del t tends to 0 and displacement along the radius vector in time del t divided by del t. Here this, when we find radial velocity, we know that radial velocity is the displacement along the radius vector in time del t divided by del t. From the figure we can see here PL is the displacement in time del t. We can see here when this particle moves from P to Q point, this takes the time del t, and in del t time it covers the displacement PL along the radius vector OP. So this is equal to, here the displacement is here PL in time del t, and from figure we can see that this PL is obtained when we subtract OP from OL. So we write here, in place of PL we write here OL minus OP divided by del t. And we know that this OL is equal to OQ cos del theta. So we write here OQ cos del theta minus OP divided by del t. And OQ is the radius vector, which is equal to R plus del R, and we know that expansion of cos del theta is 1 minus del theta whole square by factorial 2 plus del theta whole power factorial 4 and so on, and minus OP, this is equal to small r divided by del t. Now del theta is very small quantity, so neglecting this, del theta is small, so neglecting del theta square and higher power. Now we get here radial velocity, this is equal to limit del t tends to 0 r plus del r multiplied by 1 minus r divided by del t. We can see here we neglect the del theta whole square and higher power of del theta. So we get here r plus del r multiplied by 1 minus r. We can see here this r is cancel out. So we get here del r by del t, and when we take the limit of del r by del t,